According to the National Electrical Code, specifically Section 300.3b, neutral conductors must not be installed in a separate raceway from the phase conductors they are associated with. This requirement is crucial for ensuring proper electrical system operation and safety. There are several reasons why this rule exists. Firstly, it addresses impedance considerations. When phase and neutral conductors are run in close proximity, typically within the same conduit or raceway, the impedance of the circuit is controlled and predictable. This is because the magnetic fields produced by the alternating current in the phase conductors are largely cancelled out by the opposing magnetic fields produced by the current in the neutral conductor. This cancellation effect reduces the overall impedance of the circuit, which is essential for efficient power delivery and proper operation of overcurrent protection devices. Secondly, running phase and neutral conductors together minimizes the inductive reactance of the circuit. Inductive reactance is the opposition to the flow of alternating current caused by the inductance of the circuit. When conductors are separated, the inductive reactance increases, leading to voltage drops and reduced system efficiency. By keeping the phase and neutral conductors close together, the inductive reactance is minimized, improving voltage regulation and overall system performance. Thirdly, the requirement helps to prevent overheating of the conductors and the raceway. When phase and neutral conductors are run separately, the magnetic fields produced by the phase conductors can induce circulating currents in the metallic raceway. These circulating currents can cause the raceway to heat up, potentially damaging the insulation of the conductors and creating a fire hazard. By running the phase and neutral conductors together, the magnetic fields are largely cancelled out, minimizing the circulating currents and reducing the risk of overheating. Fourthly, it is important to understand the implications of this rule for multi-wire branch circuits. A multi-wire branch circuit consists of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit. These circuits are commonly used in residential and commercial buildings to provide multiple 120-volt circuits from a 240-volt source. In a multi-wire branch circuit, the neutral conductor carries the unbalanced current, which is the difference between the currents in the phase conductors. If the neutral conductor is disconnected or run in a separate raceway, the voltage on the 120-volt circuits can become unbalanced, potentially damaging sensitive electronic equipment. Furthermore, a floating neutral can create a dangerous voltage potential on the grounded metal parts of electrical equipment. Therefore, it is essential to run all conductors of a multi-wire branch circuit, including the neutral conductor, in the same raceway to ensure proper operation and safety. Fifthly, there are limited exceptions to the rule that phase and neutral conductors must be run together. One exception is for short sections of conduit used for physical protection of the conductors. For example, a short length of conduit may be used to protect conductors as they transition from a cable tray to an electrical panel. In these cases, it may be permissible to run the neutral conductor separately from the phase conductors for a short distance. However, it is important to ensure that the length of the separation is minimized and that the conductors are properly sized to handle the increased impedance. Sixthly, another exception may be allowed for certain types of control circuits. In some industrial applications, control circuits may use separate raceways for the phase and neutral conductors to minimize electrical noise. However, these applications typically require special engineering considerations and may not be permitted in all jurisdictions. It is important to consult with a qualified electrical engineer and the local electrical inspector before implementing any control circuit design that deviates from the general rule. Seventhly, when installing electrical wiring, it is crucial to select the correct type and size of conductors for the application. Conductors must be sized according to the ampacity requirements of the circuit, as specified in the National Electrical Code Table 310.15b16. The ampacity of a conductor is the maximum current it can carry continuously without exceeding its temperature rating. Conductors must also be suitable for the voltage and environmental conditions of the installation. For example, conductors installed in wet locations must be rated for wet locations. Eighthly, the National Electrical Code provides detailed requirements for the installation of electrical raceways. Raceways must be properly supported and secured to prevent damage to the conductors. The number of conductors allowed in a raceway is limited by the fill capacity of the raceway, as specified in the National Electrical Code Chapter 9. It is important to select the correct size and type of raceway for the application to ensure that the conductors are properly protected and that the raceway can accommodate the required number of conductors. Ninthly, grounding is an essential aspect of electrical safety. The grounding system provides a lower impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly clear the faults. The grounding system must be properly installed and maintained to ensure that it is effective. All metal parts of electrical equipment that are likely to become energized must be grounded. Tenthly, bonding is the process of connecting metal parts of electrical equipment together to create an electrically conductive path. Bonding is important for minimizing voltage differences between metal parts, which can reduce the risk of electric shock. The National Electrical Code provides detailed requirements for bonding electrical equipment. 11thly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overload and short circuits. These devices must be properly sized and installed to ensure that they will effectively interrupt the flow of current in the event of a fault. Overcurrent protection devices must also be readily accessible and properly labeled. 12thly, electrical work must be performed by qualified individuals who are familiar with the National Electrical Code and other applicable standards. Improper electrical work can create a serious safety hazard and can result in property damage or personal injury. It is important to obtain the necessary permits and inspections before starting any electrical work. 13thly, regular maintenance and inspection of electrical systems are essential for ensuring their continued safe and reliable operation. Electrical systems should be inspected periodically for signs of damage, wear, or corrosion. Any deficiencies should be corrected promptly to prevent potential problems. 14thly, when working with electrical equipment, it is important to follow all safety precautions. Always to energize the circuit before working on it. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work on electrical equipment in wet conditions. 15thly, it is also important to understand the concepts of voltage drop and voltage regulation. Voltage drop is the decrease in voltage that occurs along a conductor due to the impedance of the conductor. Voltage regulation is the ability of an electrical system to maintain a stable voltage under varying load conditions. Excessive voltage drop can cause equipment to malfunction, while poor voltage regulation can damage sensitive electronic equipment. 16thly, the National Electrical Code provides guidelines for minimizing voltage drop in electrical circuits. These guidelines include using larger conductors, reducing the length of the circuit, and increasing the voltage of the circuit. It is important to consider voltage drop when designing electrical systems to ensure that equipment operates properly and that voltage regulation is maintained. 17thly, in summary, the requirement to run neutral conductors in the same raceway as their associated phase conductors is a fundamental principle of electrical safety and system performance. It is essential to understand the reasons behind this rule and to follow it carefully when installing electrical wiring. By adhering to the National Electrical Code and other applicable standards, it is possible to create safe, reliable, and efficient electrical systems. 18thly, remember to always consult the latest edition of the National Electrical Code and local electrical codes for the most up-to-date requirements and regulations. Local amendments may exist that further modify or clarify the national code. 19thly, it is also recommended to seek guidance from a qualified electrical inspector or engineer when facing complex or unusual wiring situations. They can provide valuable insights and ensure that the installation complies with all applicable requirements. 20thly, understanding the theory behind these code requirements is equally important. For instance, the concept of mutual inductance plays a significant role in why conductors must be run together. When phase and neutral conductors are close, their magnetic fields interact, reducing the overall inductance of the circuit. This reduction in inductance minimizes voltage drops and improves the efficiency of power transfer. 21stly, consider the practical implications of running conductors separately. Imagine a scenario where a long run of neutral conductors is installed in a separate metallic conduit. The alternating current in the phase conductors will induce a voltage in the metallic conduit, creating a circulating current. This circulating current can lead to significant heat buildup in the conduit, potentially causing a fire hazard or damaging the insulation of the conductors. 22ndly, it's important to distinguish between grounded and ungrounded conductors. The neutral conductor is a grounded conductor, meaning it is intentionally connected to ground at the service entrance. This grounding provides a reference point for voltage and helps to stabilize the electrical system. Ungrounded conductors, on the other hand, are the phase conductors that carry the current to the load. 23rdly, when working with three-phase systems, it's crucial to understand the relationship between the phase conductors and the neutral conductor. In a balanced three-phase system, the currents in the phase conductor sum to zero, and the neutral conductor carries little or no current. However, in an unbalanced system, the neutral conductor carries the unbalanced current, which can be significant. 24thly, proper sizing of the neutral conductor is essential to ensure that it can handle the unbalanced current without overheating. The National Electrical Code provides guidelines for sizing neutral conductors based on the expected unbalanced load. 25thly, it is also important to consider the harmonic content of the load current. Harmonic currents are non-sinusoidal currents that can be generated by nonlinear loads such as electronic equipment and variable frequency drives. These harmonic currents can increase the current in the neutral conductor even in a balanced system. 26thly, to mitigate the effects of harmonic currents, it may be necessary to use an oversized neutral conductor or to install harmonic filters. Harmonic filters are devices that are designed to reduce the amplitude of harmonic currents in the electrical system. 27thly, another important consideration is the type of insulation used on the conductors. Conductors must be insulated with a material that is suitable for the voltage, temperature, and environmental conditions of the installation. The National Electrical Code specifies the types of insulation that are permitted for different applications. 28thly, when splicing conductors, it is important to use approved splicing methods and materials. Improper splices can create a high resistance connection, which can lead to overheating and potential fire hazards. The National Electrical Code provides guidelines for making safe and reliable splices. 29thly, it is also important to protect conductors from physical damage. Conductors should be installed in raceways or other protective enclosures to prevent them from being exposed to abrasion, impact, or other hazards. The National Electrical Code specifies the types of raceways that are permitted for different applications. 30thly, the proper installation and maintenance of electrical systems are critical for ensuring the safety of people and property. It is important to follow all applicable codes and standards and to seek guidance from qualified professionals when needed. By taking these precautions, it is possible to create safe, reliable, and efficient electrical systems that will serve their intended purpose for many years to come. 31stly, when working with existing electrical installations, it's crucial to exercise caution and to thoroughly inspect the wiring before making any modifications. Older wiring may be damaged, deteriorated, or improperly installed, which can create a safety hazard. 32ndly, it's always recommended to de-energize the circuit before working on it and to use appropriate personal protective equipment, such as rubber gloves and safety glasses. If you're not comfortable working with electricity, it's best to hire a qualified electrician to do the work. 33rdly, electrical safety is paramount, and it's essential to prioritize safety in all aspects of electrical work. By following the National Electrical Code, using proper techniques, and exercising caution, you can help to prevent electrical accidents and protect yourself and others from harm. 34thly, let's delve deeper into the specific requirements outlined in NEC 300.3b. This section addresses the installation of conductors in the same raceway or cable. The key takeaway is that all conductors of a circuit, including the neutral, must be run together in the same raceway or cable unless specifically permitted otherwise by the code. 35thly, The purpose of this requirement is to ensure proper impedance characteristics and to prevent overheating. When conductors are run separately, the inductive reactance of the circuit increases, which can lead to voltage drops and reduced efficiency. Additionally, the magnetic fields produced by the current-carrying conductors can induce circulating currents in the metallic raceway, causing it to heat up. 36thly, there are a few exceptions to this rule, but they are limited in scope. For example, short sections of conduit used for physical protection of the conductors may be permitted to run separately. However, the length of the separation must be minimized, and the conductors must be properly sized to account for the increased impedance. 37thly, another exception may be allowed for certain types of control circuits, where separate raceways are used to minimize electrical noise. However, these applications typically require special engineering considerations and may not be permitted in all jurisdictions. 38thly, it's important to note that the term raceway encompasses a wide range of enclosures, including conduit, tubing, and cable trays. The National Electrical Code defines a raceway as an enclosed channel designed expressly for holding wires, cables, or busbars, with additional functions as permitted in this code. 39thly, when selecting a raceway, it's important to consider the environmental conditions of the installation. For example, raceways installed in wet locations must be listed for wet locations and must be made of a corrosion-resistant material. 40thly, the fill capacity of the raceway is also an important consideration. The National Electrical Code specifies the maximum number of conductors that are permitted in a raceway, based on the size of the raceway and the type of conductors. 41thly, exceeding the fill capacity of the raceway can lead to overheating and potential damage to the conductors. It's always recommended to consult the National Electrical Code tables and calculations to determine the appropriate size of the raceway for the application. 42ndly, in addition to the requirements of NEC 300.3b, there are other code sections that address the installation of neutral conductors. For example, NEC 250.24c specifies the requirements for grounding the neutral conductor at the service entrance. 43rdly, the neutral conductor must be grounded to a grounding electrode system, which consists of one or more grounding electrodes such as ground rods, ground plates, or underground metallic water pipes. The grounding electrode system provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to quickly clear the fault. 44thly, it's also important to ensure that the neutral conductor is properly bonded to the metal parts of electrical equipment. Bonding is the process of connecting metal parts together to create an electrically conductive path. 45thly, bonding helps to minimize voltage differences between metal parts, which can reduce the risk of electric shock. The National Electrical Code provides detailed requirements for bonding electrical equipment. 46thly, in summary, the installation of neutral conductors is governed by a number of code requirements, including NEC 300.3b, NEC 250.24c, and other sections. It's essential to understand these requirements and to follow them carefully when installing electrical wiring. 47thly, by adhering to the National Electrical Code and other applicable standards, it's possible to create safe, reliable, and efficient electrical systems that will serve their intended purpose for many years to come. 48thly, when dealing with electrical systems, always prioritize safety. Never work on live circuits, and always use appropriate personal protective equipment. If you are not comfortable working with electricity, hire a qualified electrician. 49thly, remember that electrical codes and standards are constantly evolving, so it's important to stay up to date on the latest requirements. Consult the latest edition of the National Electrical Code and local electrical codes for the most accurate and current information. 50thly, electrical systems are complex and require careful attention to detail. By understanding the fundamentals of electrical theory and following the code requirements, you can ensure that your electrical installations are safe and reliable.